In this work, a reinforcement learning based approach is presented to learn robotic grasping tasks. Modern industrial robots operate in very structured environments and execute repetitive movements, but they cannot deal with the unexpected changes in the environment. For these robots, the common approach involves each action of the robot being manually programmed by an expert. Collaborative robots, on the other hand, are increasingly required to work alongside humans and adapt their behavior due to unexpected variations of the environment. Therefore, it is not possible to explicitly program all possible scenarios. The robot must act intelligently. In order to bridge this gap, machine learning approaches offer a solution and to realize smart robots. The main research goal of this work has been to investigate and propose a learning based methodology for a robot to learn and perform an industrial manipulation task. The task that is considered in this work is a grasping task that requires the robot to approach the part, grasp it, and then lift it off the contact surface. The approach consists of an agent that interacts with simulated environment. At every time step, the agent samples the state of the environment, performs an action, and receives a reward. The objective is to learn the policy, which is stochastic and represents a conditional probability distribution of actions given states. To learn the policy, proximal policy optimization algorithm is used. For every update, the state, action, and the reward is sampled from the replay buffer, and optimization objective is applied in the policy improvement phase. In the policy evaluation phase, the value function is trained for performing each policy update. After performing each policy update, the replay buffer is cleared of the past data since proximal policy optimization is a non-policy algorithm. The actions include joint actions and gripper action that are passed to the controller before being executed in the environment. In contrast to many other works, the control policy in this work is learned without constraining the working space of the robot, and the loop is closed around kinematic state only. In order to reuse the learned control policy, the idea of transfer learning is then applied to initialize the learning in modified task settings. Here the learning process can be seen. At the beginning, the motion is completely random when the networks are initialized, but as the training progresses, the learning agent learns to monotonically improve the reward and the robot gets closer and closer to complete the target task. Each episode lasts for 600 steps and corresponds to 2.5 seconds of real world time. The policy is trained for a total of approximately 10 million steps before performing evaluation. After training the control policy, the learned behavior is evaluated on 4 different scenarios by executing 10 test trials. The policy was initially trained only on a nominal cube. The other 3 parts are added to assess the generalization capability of the learned policy. Learned model can successfully grasp and lift all 4 objects in 10 test trials, despite being trained only on a nominal cube. For example, here the learned policy is shown grasping a screwdriver that was not shown during the training. Furthermore, the ability to perform the task is evaluated in the presence of position variations. In the first test, a random noise is added to the initial position of the robot at the beginning of each episode. The robot is still able to successfully complete the task in 8 out of 10 trials. In the second test, the nominal position of the part has been changed. For this specific case, 20 trials are performed, 10 for each direction. In the failed trials, the robot either grasped the cube at the edges, resulting in unstable grasp, or collided its gripper with the cube and was not able to grasp. In the last test, the model is tested for its adaptation capability by changing the part position and fine-tuning the previously learned policy. Within 30 minutes of additional training, the policy is able to successfully adapt to the changes in environment. To summarize, in this work, the task learning is formulated in the form of a reinforcement learning problem, and the control policy is learned based only on kinematics information. The performance of the learned task has been evaluated, and it has been shown that transferring the parameters of the neural networks can improve the sample efficiency for reinforcement learning in partially new task settings.